So he designed an experimental matrix so that he had various combinations of this optimum water, rain, sunshine, fertilizer, soil conditions, everything to provide or to obtain the best crop. So this DOE, the main objective of this is to optimize the process. The optimization is nothing but obtaining the best out of the available resources. I have a limited resources, and from that limited resources, how we are going to obtain the best by means of or by methods of experimentation. So this DOE is a experimental methods with an objective of optimizing the process with the available resources. So this DOE normally refers to the process of planning, how you are going to plan the experiment, how you are going to design the experiments. After designing the experiments, we have to perform the experiments, and then we are going to measure or determine the outputs and how that outputs are being analyzed. Based on these things, we are going to come to a conclusion which will provide a valid outcomes that will be more efficient and effective. So once we are going to experiment a method or a process, the main thing that we require is the better understanding of the process in which we are going to experimenting. So while performing a experimental or experiment, some process variable should be changed intentionally. Right? By varying these process variables intentionally, the output tends to vary, whether it may be in the decreasing trend or it may be in the increasing trend. So by varying the process variables, how the output is varying, that you are going to determine. So the methods of experimentations, the first foremost method of experimentation is trial and error method. So how I am going to think that I am going to do it as an experiment. There is no logic in that, just I am having an idea and I am going to do it, and that is the trial and error method. Then single factor experiment. In this, you want to have many factors or input parameters that I am planning to do the experiment. All the other parameters should be kept constant and only one factor has to be changed at a time, and that is a single factor experiment. In the factorial experiment design, we have two types. One is full factorial, in which we are going to change many factors at a time, that is the values at a time. In the fractional factorial also, we are going to change many factors at a time, but when comparing to the full factorial design, the fractional factorial experiments will have lesser number of experiments. In detail, we'll see later on. And the other designs which we are going to apply for experimental methods is Taguchi's based DOE, then response surface methodology, then Box-Jenkins methods, and there are many methods. Some of them only it is being listed here. There are many methods, so we can experiment by adopting any one of these methods. So first we will see the trial and error method in detail. So this is the most basic form of learning. If I don't have any idea to how to perform an experiment, so better it is to start with the trial and error method. So in some cases only it is efficient or applicable. If the number of parameters is higher, then this trial and error method will not produce a better output or an outcome. The example that we can use for this trial and error method is finding the combination of a log. Initially, I am going to have one trial. This same trial I can also be used in the later on session or I can go with the different combinations. That we doesn't know because it is a trial and error. So the same experiment also get repeated. So finding the best combination of the log. So in a flowchart way, we are going to present what is trial and error. So I have some thinking on my mind, and based on that, I am going to experiment. And with the obtained results, once again I am going to think, and I am going to experiment the same process, and again I am going to improve. The problem with this is it's a time consuming process. It's a time consuming process. So the limitations of this trial and error methods are it lacks direction and focus, because what I am going to do, what I am doing, I doesn't know. Just it is a trial. It's a guesswork. It doesn't have any logic. I am going to guess and I am going to implement it. How many different permutations exist? If it is a single parameter or two parameter, it is acceptable. But when the number of parameters, the parameters is input factors. The input factors, if it tends to increase, then obviously how many permutations that will exist. So we have to do many number of experiments, higher number of experiments. So the same thing, if I'm going to add more variables, the number of trials or number of experiments will get increased. So that is the main limitations of this trial and error. Then coming on to single factor experiment. So only one factor should be changed at a time during the experiment, while the other parameters, that is, for example, if I am going to consider a turning operation, normally we use the machining parameters as input, and other parameters we can add later on, that's not an issue. But the machining parameters we normally consider is cutting speed, feed rate, and depth of cut. In the single factor experiment, the cutting speed has to be varied, while the feed rate and depth of cut should be maintained at a constant values. Or if I am going to vary the feed rate, then the cutting speed and the depth of cut has to be maintained at a constant value. So only one parameter can be varied. So the main assumption in this experiment is to isolate the changes in the response variable. The response is nothing but the output. So by varying one parameter, how the output changes, that we are going to determine. So we are going to isolate the changes. So these types of single factor experiments are lengthier, but at the same time it is simple to analyze. So by varying only one factor at a time, what effect that change in value? For example, I am going to consider two values for cutting speed, 100 meter per minute and 200 meter per minute. Initially, I am going to carry out the work or the experiment with 100 meter per minute, and I am going to determine what is the tool wear and what is the material removal rate. Then in the second experiment, I am going to change the cutting speed to 200 meter per minute, and I am going to do the experiment and I am going to determine what is the tool wear and what is the material removal rate. Obviously, these two outputs, the tool wear and material removal rate, will get changed because of increase in cutting speed. So by changing the cutting speed, the tool wear and the MRR tends to increase or decrease. So it depends on the other conditions also. So that we are going to identify. But the only limitation of this single factor experiment is it's a time consuming process. So because higher experimental trials has to be carried out, which will end up in fatigue and also loss of material, loss of time, loss of power, loss of money, everything. The only issues with the single factor experiment is no interaction effects between the selected inputs cannot be analyzed. Because for example, the cutting speed and feed rate, if I am going to change it simultaneously, then the interaction levels can be determined. So this is an example for the single factor experiment. The second column represents the speed, then third one is the temperature, and fourth one is the tire pressure, and fifth one is the chassis design. That is 4 inputs I am going to have, and at each and every input I am going to have 2 values. That is the 2 level values. We call it as levels. In speed, the level 1 value is 65 and the level 2 value is 70. Similarly, for temperature, the level 1 value is 75 and level 2 value is 85. Tire pressure, level 1 is 32 and level 2 is 27. In chassis design, there are 2 different designs, A and B. In this, the speed, temperature and tire pressure are numerical values. You can see it is in numerical values, whereas chassis design is in A, B and C. It is in A, B and C. So these A and B are called as categorical parameters. In the first 2 experiments, experimental trial, that is experiment number 1 and 2, the temperature, tire pressure and chassis design are kept as constant, whereas the speed is varying. In the experiment number 1, the speed is set as 65, and in the experiment number 2, the speed is set as 70. That is, at a time, I am going to vary only one input parameter, while the other parameters are kept as constant. Coming on to experimental number 5 and 6, the temperature tends to get varied. Instead of 75, I am going to have 85. So I am going to change the temperature and I am going to set it to the level 2, and again I am going to vary the speed as 65 and 75. Similarly, you can see all the 16 combinations. Coming on to the factorial experiments, so simultaneously I can change more than one parameter, and that is the factorial design. So here it involves more than one independent variables in the study. So this factorial experiment is widely accepted for experimental, not only by researchers but also by the manufacturing firms at 2-level and 3-level designs. Both full and fractional factorial designs can also be used here. The 2-level designs are, in speed I have 2 values, 65 and 70 only. If I have another value, 65, 70, 75, then it becomes a 3-level value. That is 3 values for an input. That becomes the 3-level value. Normally, in between 2 levels and 3-level values, only 2-level values are widely used because it is very, very easy to design, efficient to run, and it is very, very straightforward to analyze. If I am going with the 3-level values, the design becomes complex. Higher number of experimental trial has to be carried out, and then the analyzing becomes a issue. The problem with the single factor experiment is the interaction effects cannot be studied between the selected input variables, which is eliminated by this factorial design. By this factorial design, the joint effect of the factors, that is the interaction effect. Cutting speed will have an effect on tool wear. Like that, feed rate will also have an effect on tool wear. But what is the combined effect? By combining the effect of cutting speed and the feed rate, the tool wear will tend to increase or decrease. So that combined effect is known as the interaction effect. So as told earlier, the factorial designs can be either full or fractional factorials. Even though it is full or fractional, all the possible combinations can be incorporated in this design. So all the multiple factors that we have considered are adjusted simultaneously in this fractional design. So that is the main success of these factorial designs. By controlling multiple factors, the total number of experiments tends to reduce. That's the advantage of this. So, and also the complex interaction effects between the selected input parameters will also be revealed. So among the various input parameters that we have selected, which parameter influence is higher? For example, in turning, cutting speed, feed and depth of cut, among these three, which is more influential? That we can identify by using this factorial experiment. So here we have see a table consisting of different runs on the y-axis, 4, 8, 16, 32, 64. On the upper x-axis, we have 2, 3, 4, 5, 6, 7. And that are number of input variables. The upper x-axis is the number of input variables and the y-axis is the number of experimental runs. For two variables, the number of experimental trial is 4. That is 2 power 2. Normally in factorial design, we have 2 power k. So 2 power 1. So 2 power 2. Since it is two variables, 2 power 2, which is equal to 4. But for 3 parameters also, we have 2 power 3 minus 1, which is equal to 4. That is represented in red color. And below that, we can see a symbol 3. Roman symbol 3. That I will tell you later on what is that. Similarly, in the white boxes, that represents the full factorials. The white boxes represent the full factorial. For example, look into the 4 variables. The 4 variable is 2 power 4, that corresponds to 16. Similarly, for 5 variables, I can use 8 experiments, 16 experiments or 32 experiments. If I am going to consider 32 experiments for 5 variables, then it becomes a full factorial. In the same case, if I am going to consider 16 experiments, then it becomes a fractional factorial. If I am going to consider 8 experiments for 5 variables, then it is also called as a fractional factorial designs. Why this changes? That we will see later on in this presentation. So design resolutions. So it is the summary characteristic of aliasing or confounding. Confounding is nothing but inability to estimate some effects or interactions. If it is aliasing or confounding, some effects will not be estimated because of the inability. Okay, for designed experiments, we have up to 10 aliasing factors. But normally we are interested only in resolution 3, 4 and 5. In the previous also, in the table we have seen that 3, 4, 5 also. So what is meant by resolution 3? What is meant by resolution 4? What is meant by resolution 5? That we are going to look into now. So what this design resolution actually identifies? This design resolution identifies the specific design, the order of confounding the main effects and their interactions. How the main effects and the interactions are being studied. If it is going to study only the main effect, if it is going to study only the 2 factorial interactions, or if I am going to study the 3 factor interactions, that depends upon the resolutions. The resolution 3 designs, the main effect is not compounded with the main effect, another main effect. That is, in a turning operation, cutting speed, feed, depth of cut. So the main effect of cutting speed will not have any compounding effect on the feed rate. But main effects are compounded with the 2 factor interactions. The cutting speed has a compounding effect in between the interaction effect between the feed rate and depth of cut. Similarly like that. And similarly, the 2 factor interactions will have the compounding effect on the other 2 factor interactions also. That is, in between the cutting speed and feed rate, there is one interaction, and between feed rate and depth of cut, it has another interaction. These are 2 factors. And between cutting speed and depth of cut, another interactions. So 3 2-factor interactions are there. So in between them, the aliasing will be there. And that is the resolution 3 designs. Similarly, for resolution 4 designs, the main effects are not compounded with another main effects or other main effects, and also with the 2-factor interactions. But the two-factor interactions will have an aliasing effect on the three-factor introduction. Coming on to resolution 5, we don't have a compounding effects between the main effects and between the two-factor interactions, but the two-factor interactions are compounded only with the three-factors interactions. Coming on to full factorial experiment. So this full factorial experiment consists of all possible combinations of the selected inputs that we are going to experiment. If I am going to have k factors, the k factors is nothing but the number of inputs. As in the turning experiment, cutting speed, feed, depth of cut. So the number of k is equal to 3. That is 3 inputs. Each at 2 levels, the full factorial consists of 2 power k designs. In our work, in the turning operation, the number of inputs is 3. So 2 power 3, which is equal to 8 experiments. But the drawback of this full factorial design is it is a time consuming procedure, but precise data analysis is possible with this. So we should know this 2 power k in all the full factorial experiments at 2 levels. If it is 3 levels, then this formula will become 3 power k, where 2 is the level and k is the number of inputs. What are the benefits of going with full factorial design? So, which level value has the influence on the output? That can be easily determined, because the effect of each factor mainly depends upon the value that we are going to select for experimental. So, what is the value that is being selected for experimental will have an impact on the output that is being produced. So, the effect of each factor mainly depends upon the value that we are going to select in this experiment. So, these full factorials are specifically useful for excellent precision for the developed regression models. The regression models are nothing but the mathematical model that we are going to develop because of experiments, that is known as empirical models. By this full factorial experiment, excellent precisions can be attained along with the combined effects of the factors. The full factorial is specifically useful whenever I am going to study the individual effects as well as the combined effects of the input parameters. So this is an example for the full factorial experiment. The purpose is to make tasty popcorns. The popcorns are made from corns. Everyone knows that. So here I am going to select 3 inputs and I am going to measure 2 outputs. The first input is the brand. So brand of the corn that I am going to purchase, the time for frying and the power that is being required. And the outputs that I am going to measure is how the taste of the popcorn is obtained. What is the taste of the obtained or fried popcorns? Then how many bullets are there? The bullets are nothing but unpopped corns. For popcorns, the corns has to pop up. If the corns is not popping up, then it is called as bullets. So in each and every inputs, I have 2 levels. In brand, I have costly and cheap. In time, I have 4 minutes and 6 minutes. In the power, 75% and 100%. So 2 power 3, because I am having 3 inputs, that is k is equal to 3 and number of level is 2. So 2 power 3, the number of experiment is 8. So this becomes a full factorial experiment. And based on this designed factorial experiment, I am going to perform the experiment and then I am going to measure what is the taste and how many bullets are there in that. So in the table, the first column we have standard order and in the second we have the run order. The run order is used for randomization. The randomization reduces the experimental error. For this purpose only we are going to use the run order. The standard order is the designed order. So normally we will be dealing with the run order only. So this is another example. Here I have 4 inputs and each input is varied by 2 level values. So k is equal to 4 and the number of level is 2. So 2 power 14 is equal to 16. So cutting speed is varied by 2 levels, 100 and 200, and feed rate is 0.25 and 0.75. Then depth of cut is 0.3 and 0.6, and type of how you are going to supply the coolant, whether it is flood cooling or minimum quantity lubrication. The other name for MQL is mist cooling. So how you are going to supply the coolant? So I have developed a 16 experimental trial, full factorial experimental trials. And the first experimental trial I am going to set on the machine with a cutting speed of 100, feed rate of 0.75, depth of cut of 0.6 and coolant flood type. And I am going to perform the experiment. And I am going to measure the surface roughness of the machined surface in microns, and I am going to determine that. Similarly, I am going to measure for all the 16 experiments and I am going to record. And further we can do the analysis. Then coming on to fractional factorial experiment, these fractional factorial experiments are being run or fewer runs than that of the full factorial designs based on the design resolutions. So design resolutions normally we are going to consider is 3, 4 and 5 depending upon the confounding effects between the main effects, the 2-factor interactions and 3-factor interactions. But when comparing that with the full factorial, lesser experimental trials is adopted in fractional factorial experiment. So this is an appropriating experiment in which I am going to have 5 inputs. For each and every input I am going to have 2 levels. So k is equal to 5 and level is 2. So normally in full factorial we are going to have 2 power 5. But they have designed the experiment for 16 experimental trials. So 2 power k is equal to 2 power 5. So in full factorial conditions we have 32 experimental trials. But I am going to consider only 16 experiments based on the resolution 5. Once again I am going back to that image. So here you can see I am going to have 5 variables. In 5 variables for full factorial it is 32, 2 power 5. But I am going to have only 16 experiments. So 2 power 5 minus 1, the resolution is 5, that is given in green color. So if I am going to consider 16 experiments, then it is resolution 5. Then if I am going to consider 8, then it is resolution 3. But in these experiments, they are considered the resolution 5. So minus 1 is the low value and plus 1 is the high level value. So minus 1 corresponds to 20 of temperature and plus 1 corresponds to 50 of temperature. So based on this, they are going to measure the outputs and then they are going to analyze. So this is the another example for fractional factorial experiments. So how much distance that we are going to cover in a specific time period by using different settings in a bike. The first parameter is seat, the second one is pressure of the tire, and third one is the position of the handlebar, then brand of the helmet, then gear position and wheel covers, and then generator. So 7 inputs I am going to have. In each and every input I am going to have 2 level values. Normally in full factorial design we are going to have 2 power 7 which is equal to 128 experiment. But we are going to end up with just 8 experiments in the fractional factorial experiment. with all the possible combinations by adopting design resolution 3. You can check that with the table and you can see this 8 experimental trial values. Then coming out of the experimental design, so these are some of the experimental designs that we have seen earlier, and now we are going for the statistical design of experiments. The purpose of this, any design of experiments, is to plan experiments to obtain a valid and efficient and effective conclusions. The main purpose of this is to yield a valid and objective conclusions. And how we are going to perform this experiment? By varying the levels of individual factors, that is the selected input parameters, simultaneously with that of the other selected parameters. For example, in turning operation, cutting speed, feed, depth of cut, by varying the level values of cutting speed, and simultaneously I have to vary the level values of feed rate also. So by varying this, what will happen is the efficiency of the system gets improved, and also the cost associated with the experiment will get reduced. The time associated with the experiment will be getting down, and also we are, apart from the main effects, we are also going to study the interaction effects also. So that is the main thing. In all the process, not only the main effect, but also the interaction effects among the individual input parameters are very, very essential in determining the output of the process. So these interactions are the driving processes. So while designing an experiment, apart from main effects, we have to study the interaction effects also, which is very, very essential. So this experimental design economically maximizes the information, because with the reduced time, with the reduced cost, the cost is nothing but experimental cost, then material cost also. Because if I am going to carry out 16 experiments, then obviously it will take around 3 hours, for example. So 16 individual workpieces I should have. So the machine has to run for 3 hours. But then reduced design of 9 experiments, so 7 experimental cost is being reduced. So the time may be reduced to 1 hour or something. So economically it maximizes with respect to the information. So in normal experimental designs, the first thing what we have to do is formulation of the problem. So what problem that you are going to formulate, whether it is a single objective or multiple objectives. The single objective is only one output I am going to analyze, whereas in the multiple objectives, more than one output I am going to analyze. In the turning operation, number of outputs that we are going to determine or calculate may be different. For example, tool wear, material removal rate, surface roughness, cutting forces. There are many outputs. If I am going to consider only tool wear, then it becomes a single objective. Along with tool wear, if I am going to consider material removal rate and surface roughness, then it becomes multiple objectives. In the single objective and multi-objective problems, it may be further classified into constrained and unconstrained problem. In constrained, if the output is set to a specific target, then it becomes a constraint. For example, the surface roughness should not go beyond 4 microns. That is, I am going to target the value of the surface roughness to 4 microns. And that becomes the constraint optimization. If I am not going to set a value for the output, then it becomes an unconstrained optimization problem. In the variable classification, we have continuous and discrete. In the continuous category, the input cutting speed varies between 100 rpm to 200 rpm. So it takes any value in between 100 and 200. So it becomes a continuous. But in the case of discrete, in the example we have seen, the chases is of two types, A and B. Whether it will be A or it will be B. There is no values in between that. So that becomes a discrete value, or it is a categorical value. In the function classification, it may be a linear or non-linear. It may be convex or non-convex, or it may be differentiable or non-differentiable. It all depends upon what type of problem that we are going to study. What type of problem that we are going to study. So in the formulation of problem, the model that we are going to develop should describe the economical aspects and the exact representation of the real system. So the exact representation of the real system should be made as a model with the economic descriptions and all these things. So in order to develop a optimization model, the process should be divided into 5 major parts. The first part is the data collection, then definition of the formulated problem, then developing the model that we are going to test, then validating the model and evaluating its performance. If the performance is not good enough, then once again I have to redefine the problem. If the performance of the system has got improved, then it is okay. If it is not improving, then redefine the problem and once again develop a new model and then validate the model. Upon improving the performance, the problem should be interpreted and it should be applied. So this is an injection molding example. The injection molding part has many inputs, among them the mold temperature, the gate size, the holding pressure, the screw speed, percentage of regrind, and type of raw material that we are going to use will have an impact on the length of the molded part, the width and the thickness of the molded part. The molded temperature mainly depends upon the raw material that we are going to use in the injection molding parts. With this thermosetting and then thermosets, it will vary. The gate size is nothing but the opening size of the injection molding. The holding pressure, with which pressure I am going to inject the molding parts into the die. The speed of the screw. So everything will have an impact on the length, width and thickness of the molded part that we are going to produce. So we should be very, very careful. So here comes the data collection. So what should be the molded temperature? What should be the gate size? What should be the holding pressures? So the data collection maintains the important part of any problem. Then I am going to formulate the problem. My formulation is I should have a higher length molded part, higher width or higher thickness. So in order to obtain this, these input parameters I am going to vary. So for this I am going to develop a model, then I am going to do the experiments and then I am going to validate that model. If the performance increases, then I can apply that. In any model, physical model, we have inputs and outputs. The system will be subjected to controllable variables and the uncontrollable variables. The controllable variables can be controlled in nature, and the uncontrollable variables are signal or noise variables which cannot be controlled. In the previous example, the mold temperature, gate size are the inputs, and the outputs are length, width, and the thickness of the molded parts. The control variables are such that the raw material can be controlled. The raw material composition can be controlled. That can be controlled. The uncontrollable variables are the vibration of the machine. If it is a new machine, the vibration will be less. But upon usage, due to depletion and wear and tear, the machine tends to vibrate, which is a noise variable. So obviously it cannot be controlled. So a system comprises of input and outputs along with the controllable and uncontrollable variables. So the controllable variables can be varied easily during the experiment, whereas the uncontrollable variables are very difficult to control during an experiment. So we should identify what are all the uncontrollable variables and we should keep it within that limit. So that is very essential in doing an experiment. So because of this controllable and uncontrollable variables, the variation in product performance changes and it is inconsistent in nature. So these uncontrollable variables are the noise factors. So that should be limited as much as possible. The controllable variables can be changed. The controllable variables can be changed during that settings and then the output can be determined. So the principles of experimental design is randomization, replication and blocking. In any experimental designs in DoE, we will come across these three principles. The purpose of this is to improve the efficiency of experimentation so that the experimental error tends to lower or becomes nil. So for this purpose only we are going to use these three principles: randomization, replication and blocking. So in order to reduce the experimental bias or experimental errors only, these principles are going to be used. So what is meant by randomization? So we are in a realistic world in which things are non-stationary. That is, external disturbances will be higher. So these external disturbances are known as noise factors, which we cannot control. So by randomizing the experiments, these noise factors can be reduced. We cannot eliminate, but we can reduce. The purpose of randomization is to reduce the effect or influence of the experimental bias because of the noise. So the purpose or the objective of this randomization is to eliminate or remove all external variation sources or external variation sources that are not controllable in real life settings. Normally we cannot eliminate, but we can reduce the influence of the noise variables by this randomization approaches. For example, if I am going to consider a manufacturing process that involves 4 M's: men, method, materials, and then machineries, in which the attitude of the peoples who operate the machines vary from time to time because the humans are emotional in nature. Whatever that happens around themselves will have an impact. So the attitudes of the people will get changed. So that is a noise factor that is uncontrollable in nature. Then coming on to replications, the replications are nothing but the repetition of experiments. Repetition of experiments. The purpose of repetition is to reduce the experimental errors. Because whenever we are going with a manufacturing firm, the components are produced between different batches of the same day will not be identical in nature, because the quality of products produced between 2 consecutive batches will have difference. So that's why we need replications in order to reduce the experimental error. The entire operations or experiments can be replicated, or a part alone can be replicated in order to study whether there is an experimental error or not. If the experimental error exists, then we have to go with higher replications. So replications normally have three properties. The first property is to determine more accurate estimate of the experimental error. More accurate estimate of the experimental error. And second, to determine the most interaction effect. So that is, he is going to determine precisely the factor and the interaction effects. And the third property is to remove the errors because of the experimentations. With the repeated experiments, if I am going to end up with the same results or nearby results, I can conclude that the experimental error is nil or low. If there is a high experimental error, then I have to change the machine settings or the process settings. The limitation of this replication is it is a time consuming process. For example, if I am going to run 9 trials, for single experiment, I will end up with 9 experiments. If I am going to replicate all the 9 experiments, then it becomes 18 experiments. If I am once again going to replicate trials, then it becomes 27 experiments. That is, by increasing the amount of replications, there is a substantial increase in the time. Along with the time, the power will get increased, the manpower, in the economical aspects also, it is not that much feasible with going with higher replications. So, if the material is expensive, replications may lead to exorbitant materials cost. So, it is very, very essential when the replication is required or needed. Just like that, we should not go with the replications. If it requires, then only we can replicate a portion of the experiment or the full experiments. So, we should be very, very careful in that. So, many researchers use these two words, replications and repetitions, interchangeably. So, these two are one and the same, repetitions and replications. Then comes the blocking. The purpose of blocking is to eliminate the extraneous variation. For example, if there are 3 persons who are going to do the experiments, or 3 different time frames I am going to do the experiments, and I have to block experiments for one time period, and second set I am going to block it for the next time period likewise. The purpose of blocking is to remove or eliminate the unwanted sources of variability. The variability comes from the batch to batch, day to day, or shift to shift. For example, in a shift, I am going to have 3 batches. I am going to produce 3 batches. In between the 3 batches, there will be some variations, that is batch to batch. In a day, there will be 2 shifts. So the products or parts that is being manufactured from in the first shift will vary with the products manufactured in the second shift. So that is shift to shift. Today, tomorrow, and day after tomorrow. So 3 days I am going to perform the process, and there will be certainly some variation will be there. So in order to eliminate these variations, I am going to block the experiments. So the idea is to arrange similar experimental runs into blocks. So by blocking, I am going to remove the variation that comes from the experiment. So observations collected under the same experimental conditions are said to be in the same block. So with the similar experimental conditions, I am going to put it in a block. So by doing experiments, if it is in the blocking, perform the things in the first block in a continuous manner. don't go for any breaks. So first we have to finish the experiments in first block without any break. If you require break, finish the first block. Then in the second block we can take some break and then we can perform that. Thereby we are going to reduce the experimental errors. So process variable selections. So the process variables include both the inputs and outputs. The inputs are called as parameters or factors, and the outputs are responses. So the selection of this variable is better to be identified and selected based on a team effort, because the input that what I think is a better one will not be a good based on the experience of the next person. So collectively the decision has to be made, and then only we have to select the inputs and the outputs. So the team should include all the important factors that have an influence on the outputs determined based on the engineering aspects. So we should be bold enough in selecting the variables, or just like that we should not select the inputs and outputs. Regarding selecting the level values of an input, for example, selecting the cutting speed level values, there are many handbooks or previously done works. So based on that only we have to select. Just like that we should not select. Any values that we are going to select for experimental should be defined in a clear manner. So we have to be bold in that. So check for the factor settings that are impractical in nature. For example, if I am going to select a cutting speed of higher range, 5000 RPMs in an ordinary central lathe, it is impractical in nature. So that types of impractical or impossible combinations has to be eliminated. So we have to include all the relevant responses. For analysis, the efficiency of the process mainly depends on the inputs and the output that is being measured. So by doing experiments, I have to determine or calculate what are all the possible responses that I can obtain. Then only a perfect picture about the process improvement can be made. So with this, we come to the end of some of the basics about DoE. If you have any doubts in this, you can raise and I will answer to your questions.